We're very close to having a full-fledged model of how musculotendon units operate in the body to produce force. So as a review of what we have seen so far, we've got a muscle, which we can conceptualize as one gigantic sarcomere going from a tendon to the origin of the muscle, coming off that tendon at some pennation angle. That muscle, which is, it's approximately one big sarcomere, more or less, or it behaves that way. It has a few very important defining properties. One of them is the optimal fiber length, and that's just an intrinsic property of a muscle. You measure that in a cadaver study or something. Another one is the maximum isometric force production capability, and we just saw in the last video that is going to be equal to the physiological cross-sectional area of the muscle, meaning that cross-sectional area, times the specific tension of muscle, which is just you can think of it as just some number. It's just like 60 or 35 or whatever source you use, newtons per centimeter squared. And then there's also the Vmax, the maximum shortening velocity of the muscle. Again, that would be something you would do an experiment and find out and measure, or look up from some other study. Traditionally, we assume that tends to be about 10 for fast twitch muscle fibers, and I think about 3 for slow twitch. The units here are for slightly arcane reasons, we express those in optimal fiber lengths per second. There's a little bit of detail on this in the notes from week 9 if you're interested. But just a slight implementation detail is we use this strange unitless unit here. Now, one thing is missing. Well, two things are missing, but the first of which is the behavior of the tendon. So we've kind of just ignored this tendon coming off like this. But we know from the last unit that tendons themselves have their own mechanical properties. When you pull on a tendon, it stretches out like this, and it's got, as you know, it's got a toe region and it's got a linear region, and if it gets too stretched out, you get into the plastic region, and then maybe it ruptures. So we're going to modify this simple model as follows. We're going to say this tendon right here is itself like kind of a sort of special nonlinear spring, like this. And what we're going to do is we're going to take that stress strain curve we had from the last unit, which looked like this, and it was stress, meaning force, divided by cross-sectional area, and strain, which was the change in length divided by the original length. It was just a percentage change in length. We're going to modify that slightly, and we're going to make it line up with the units we use to measure this stuff. So we're going to express the force the tendon produces as a multiplier of the optimal muscle fiber force. And then we're going to express the length of the tendon in absolute terms. So maybe let me just get rid of that, and we'll move the axis. We'll move the y-axis down over here. Force is still on the y-axis, and this is just going to be absolute tendon length. Now, we saw with muscle fibers that the passive force production capability of a muscle, I shouldn't say capability, but just the amount of stretchiness in a muscle, goes to 0 once the muscle is too short, because there's no tension in those titin fibers. And I made a rubber band analogy, that if you have a rubber band and you're pulling on it, of course it's taut and it's pulling back this way. But if the rubber band is completely relaxed, it doesn't produce any force at all. Tendons, being sort of like nonlinear rubber bands, are gonna do the same thing. So imagine if you fully plantar flex your ankle and think about how much force is how much tension is in your Achilles tendon. The answer is probably 0. And that's because when your Achilles tendon gets all the way relaxed, it is not stretched out at all. It's not going to produce any tension. And this, the point at which, the tendon length at which that happens, we just call the tendon slack length. And it's called that because it's the length of the tendon at which the tendon goes slack, meaning there's no tension in it. Now, this is the units of length here are another one of those weird things where we actually express this in units of the muscle's optimal fiber length. But again, that's kind of an implementation detail that you don't need to worry about. But what we have on our screen right now is everything you need to understand the mechanical behavior of a muscle. Or maybe rather everything but one thing that we'll get to next week, which is the activation, the neural activation and excitation of this muscle. So we've been talking about everything as if the muscle is activated at 100% of its force production capability. And next week we'll talk in detail, and in some of the upcoming videos you'll see the details of how a neural signal coming in from say a neuron, a motor neuron, into the muscle fibers actually gets translated from electrical signal running down the neuron to muscle force production. And it has to do with the inflow and outflow of calcium and so on and so on and so on. But we've got plenty of time next week and later this week to talk about excitation and activation. So this here is this thing right here is our musculotendon model. And we can model pretty much any muscle in the body with these parameters, which is pretty cool.